Okay, this is the second video of linear kinetics. So we will start the friction today. Friction means force acting at the area of contact between two surfaces. For example, if I just rub this table like this, okay, I can feel something hot in between my hand and the table. That's due to friction. Okay, that's force acting at the area of contact between two surfaces. So you can quantify the magnitude of friction, okay, by multiplying mu times n. Here n means normal reaction force. Okay, normal reaction force. N came from this n, and then here mu means friction coefficient, okay? Friction coefficient, which can vary among the different surfaces. For example, here, compare this surface to the carpet. Okay? This surface is smoother than carpet, which means for friction coefficient, okay, for this one has a lower friction coefficient compared to this carpet. That's the this can vary among the different surfaces. And then you can multiply, and then normal reaction force means, okay, the force acting perpendicular to the surface. So again, normal reaction force means a force acting perpendicular to the surface. So for example, in this example, a box here, box. I'm pulling this box this way. If then the friction will be acting the opposite way, okay? So F means friction actually, and then the direction of friction will be opposite of that of the motion tendency. Which means if I pull this box this way, friction will be acting the other way, okay? That's why F here again, F here, and then friction the other way, right? And then you can actually calculate the magnitude of friction by multiplying this, as I mentioned earlier. Mu times, and then normal reaction force. Here, normal reaction force, okay? So box here, and the weight of box acting downward due to gravity, right? If then the box will be receiving same amount of force coming from this ground to this box, okay? The reaction force, okay? Is acting perpendicular to the surface, this surface. Okay, this is how we can get normal reaction force perpendicular to the surface. And then the friction can be classified into these two frictions: sliding friction and rolling friction, depending on the type of motion occurring between two surfaces. Okay, sliding friction means due to relative motion of the surface. Okay, and then rolling friction means due to temporary deformations of the surfaces. So I'm highlighting this one in red again. Rolling friction is primarily due to temporary deformations of the surface. And this example of sliding friction is an example of rolling friction. Yes, sliding friction, as I mentioned earlier here, relative motion, something like this. Okay, relative motion. Okay, and then rolling friction is due to temporary deformation. That's why this one can be example of rolling friction. Let's assume that we have a tire here, and then this is moving this way, rolling this way. Okay, if then as this tire move this way, okay, this pole will be deformed, okay, slightly, okay, temporarily, okay, and then deformation will be continued. Then by the time the deformation reach here, it will return to the shape. That's why during this time, the tire will have some sort of a deformation, but that's temporary. That's why this example of rolling friction, sliding friction and rolling friction. So if you compare these two in terms of magnitude, so this one is a lot larger than this one, okay? A lot larger than this one. Okay, this is very important for your exam. Let me give actually example of sliding friction and rolling friction. And the wheel, so as I mentioned, all wheels can be generate some sort of rolling friction. Okay, and then pyramid building here. A long time ago, the Egyptians built the pyramid. Okay, but when they built the pyramid, they had to move very heavy rocks. Okay, and then the rocks, actually, the flood arrived down the river, and then they loaded the rocks to move the rock from the river to the pyramid. And then they unload them, and then they got these big rocks on the sand, right, on the ground. And then they put actually round-shaped log underneath the very heavy or big rock, okay, to move this rock from here to there easily. Okay. But if they didn't use this round-shaped log, then it was very hard. It was almost impossible to move this heavy rock from here to there, right? Which means they just, by putting the round-shaped log underneath this rock, they were able to easily move very heavy rocks from here to there. So by putting this round-shaped log underneath this rock, okay, they just changed or converted sliding friction to the rolling friction. Without these trees or logs, okay, underneath this the heavy rock, they would have only sliding friction, relative motion between this rock and then the ground or sand. But by putting these kind of materials underneath this very heavy rock, they can convert the sliding friction to the rolling friction, which means they can reduce the friction between this rock and then this actual ground by putting this round-shaped log underneath this very heavy rock. Okay, which again, as I mentioned, that's why sliding friction is a lot larger than rolling friction in terms of magnitude. Okay, is it okay? Larger than this. And then another classification of the friction: static friction versus kinetic friction. You can classify the friction into these two. Okay, depending on the type of whether there's a motion is involved or not. Again, depending on whether there's a motion is involved or not, you can classify friction into static friction and then kinetic or dynamic friction. And the static friction means here F means again friction. Friction experienced with no motion, so without motion. Whereas kinetic friction means, or dynamic friction means, friction experienced during motion, without motion and with motion. Now I'd like to introduce one more friction, which is called maximum static friction. The force required to initiate the motion. Okay? Let me explain all these three. Okay? First of all, static friction. Let me push this table. Okay? I'm pushing this table, right? But this is not moving. Which means this one has static friction. Although force is applied, but since this friction is larger than my friction, that's why I won't be able to move this table. But still, this one has friction. There's static friction. Friction experienced without motion. How about kinetic friction? Again, I'm pushing this one again. Okay. Oh, now I can move. Okay. So friction experienced during motion. Okay, that was kinetic or dynamic friction. How about the maximum static friction? Force required to initiate motion, which means again, let me push. Okay. Oops. It's not moving. But let me simply progressively increase my force. Okay. If then at some point, I should be able to move this table. Okay. So by the time this table start moving, okay, that point, that's the maximum static friction. The force required to initiate motion. Okay, here, maximum static, this point. Okay, that's the maximum static friction. And then kinetic friction is also a force required to maintain motion. Okay? Which means once you start moving this table, and then I can keep moving this table, right? And then during the motion again, kinetic friction can also be used to maintain the motion. So the static, maximum static, and then kinetic friction, depending on whether motion is involved or not. So let me simply explain this figure. Then you will be able to understand all three types of the friction. Okay? Static friction, kinetic friction, and maximum static friction. And then whenever you have this kind of the figure, you have to understand, as I mentioned, the axis first. So horizontal axis means applied force, vertical axis means friction force, actually friction. And then here, and then graph here, graph is look like this. And then this part is static friction region, and this part is dynamic friction region. Okay, static friction and dynamic friction. Which means in this region, okay, there will be no motion involved. Whereas in this region, there will be motion involved. So then let me apply force. What if my force is just this much? This much. If then, friction will be only this much. Okay. Then my force will be equal to the friction, which means my force will be cancelled out this static friction, because my force was not large enough to move table or chair. That's why my force will be cancelled out or equal to friction, so that I cannot move the table or the chair. Okay, and then keep increasing my force. Okay, and then keep increasing my force, and then when my force is right here, my force right here, if then, that's what? Instant of motion. Instant motion. If then friction will be this much, okay? When my force is right here, friction will be this much. This is a ms, a mu s, which means, actually, mu means again the friction coefficient. Okay? The static friction coefficient, which can be used to calculate the maximum static friction. So friction is right here, okay? Instant of motion, which means this point is maximum static friction. Okay? By the time we can initiate the motion, and after that, this friction will become the lower slightly and then maintain. So this one is kinetic friction. So this is dynamic region. Here, let's compare maximum static friction and then kinetic friction. I'm not comparing static friction with the kinetic friction, but maximum static friction with the dynamic or kinetic friction. If you compare these two, so which one is higher between maximum static friction and dynamic friction or kinetic friction? Okay. So as you can see here, maximum static friction is always larger than a dynamic friction. Let me give you actually an example. Okay, we have a very big piano here. This is a piano. Okay, I want to move this piano. Okay, this is very heavy. But let me keep increasing my force. If then, at some point, I can move this piano, and then after that, I can easily this piano to keep moving. Which means the force required to initiate motion, okay, is larger than the force required to maintain the motion. That's why maximum static friction, okay, right here, is larger than kinetic or dynamic friction. Keep this in mind. So that this region, as I mentioned, okay, your force is larger than friction. That's why you will be able to move the table right here. Again, it is a static friction coefficient and kinetic friction coefficient. This one is used to calculate maximum static friction, and this one is used to calculate kinetic or dynamic friction. And then this is already larger than this. And then here I want to move almost a step farther. Okay. So we got force applied, your force, okay, and then friction. When this is larger than this, right, as you can see here, then you will be able to move the object, because your force is larger than friction. Then when this table moves, okay, according to Newton's second laws of motion, okay, when force generates movement, that movement is supposed to have what? Acceleration. Which means when something is moved by a certain amount of force, which is larger than friction, then we'll be able to calculate accelerations as well. Here I put the F net. That means overall force. or resultant force. So you can calculate this one by subtracting friction from your force. For example, friction was like 90 Newton. Okay, 90 Newton. And your force was 100 Newton. Okay, it's larger than this. Then you will be able to move the table, right? But force, net force will be how much? Okay, 100 minus 90, which means just 10 Newton will be the net force, which is equal to mass times acceleration. Which means once you get this net force, then if you know your body, the mass of this object, you will be able to calculate acceleration by simply dividing this net force by the mass information provided. So you need to understand this step. Once we move any object, okay, we will be able to calculate accelerations as well by calculating net force and by obtaining this mass information. So we'll go over a couple of maybe example of this one later when you do the review for the third exam. Now let's go over simple example of friction. Okay, right here. So you have a boy, okay, sitting on this sled. Okay, and then here W means weight of sled, weight of this boy. Okay, 200 Newton from sled, and then 250 Newton from this boy. And then we got two friction coefficient, mu s here static friction coefficient, and mu k kinetic friction coefficient. These are larger than this. So this one can be used to calculate the maximum static friction, can be used to calculate the kinetic or dynamic friction. So this is asking us to calculate, okay, how much force is needed to initiate motion. Which means this one is asking us to calculate what? To calculate maximum static friction. That's why friction is equal to mu s times how about n, normal reaction force. How much is this in this system? We got the 250 from the boy Newton, right? Plus what? 200 Newton. So total 450 Newton. Okay. Actually 450 Newton. This much force is acting downward due to gravity. But we need actual normal reaction force. Okay, which is coming from the ground to this system. Okay, so 450 should be, this one should be the 450. Must be the same as force coming from this system. All the directions are opposite. Okay, so for this one, to initiate motion, which means you need to multiply mu s is a 0.18 times 450, and then this maximum static friction, and then to maintain motion, which means how much force is required to maintain motion, which means it's asking us to calculate kinetic friction. So that we have to use this one, mu k 0.5 times 450. Again, this is supposed to be larger than this, as you can see here. As I mentioned, maximum static friction will be larger than kinetic friction. And then one more example from box pulling here. Box pulling. This is kind of interesting the question. It's highly related to the exam. So we have one box of 500 Newton. 500 Newton. Okay. And then I'm pulling this box this way. And this box will move this way. But we want to figure out whether we can move this box or not with this amount of force. Okay? This force acting this way, right? But this force can be broken down into two perpendicular components, horizontal force and vertical force, according to vector resolution as you learn. Which means I can visualize this. Okay? 5 Newton acting downward, right? And this force F here, and keeping broken down into here 100 Newton horizontally and vertically acting up 50 Newton. So acting this way and acting up, tip to tail, right? If then you'll give us the force. So you can break this force down into these two. And then these two are provided already. And then mu is a friction coefficient also provided. Okay. Mu is 0.2. But with this information, so we need to figure out whether we can move this box or not. Which means, since this box will move this way, okay, this force is important, 100 Newton. So that if this friction in this system is larger than 100 Newton, equal to or larger than 100 Newton, you will be able to move this box. But friction is less than 100 Newton, if then we will be able to move this box. Okay? Because this is my force, right? Then if you let's calculate the friction in this system, okay? If then we will be able to calculate, identify whether we can move this box or not. Okay, again, friction again, as you learn. So mu times again normal reaction force. Mu is here, 0.2. How about normal reaction force here? Reaction force. So weight of this box is 500 Newton, acting downward. At the same time, acting downward, right? And here we have one more vertical component besides this one. Which is coming from what? My force acting vertically up. So this one. Since I'm pulling this box diagonally upward, this one is acting up, 50 Newton. This acting down, 50 Newton is acting up. So total, how much force will be? 415 Newton. You have to subtract this force from this weight of this box, because these are acting opposite direction. So total normal reaction force will be 450 Newton. Multiply these two, 90 Newton. This is for friction. Friction is 90 Newton. Let's compare this value of my horizontal force. Oh, my force is larger than friction. If then, I will be able to move this box. So will it move? Yes. But I want to slightly change this condition. What if I change the direction of my force? For example, not diagonal upward but downward, like this. For example, same thing, but now diagonally downward. It still is a 100 Newton horizontally, but this time, since I'm putting this down, the diagonal downward, okay, this is acting down, right? So this is 1 Newton and acting down, 50 Newton. It's acting downward. This is also acting downward, Which means friction will be 0.2 times actually 550 Newton. Why? I just change the direction from diagonal upward to downward. Which means now this vertical component of my force will be acting downward. That's why these two are acting the same direction. That's why we have to add these two to get this one. Which means for a given object and for a given force applied, depending on the direction of the force, friction will be different. This is different from previous example, right? 450 Newton in terms of normal reaction force, depending on the direction of my pulling force. So when we pull something diagonal upward, will generate less friction compared to when you push something downward. So that's why whenever you move something, you do better pull the object instead of pulling the object. Okay, it's easier to move something if you pull the object compared to when you push the object. Okay, so keep that in mind. For a given force, depending on the direction of this force, friction will vary. It's important for exam. Let's keep this in mind. And then friction strategy. There are different friction strategy. Okay. Sometimes you have to minimize friction. Sometimes you have to maximize friction, depending on the situation. So minimize friction as a resistance. For example, in the synovial joint, for example, knee joint, we have a synovial fluid in it. So which will serve as like a lubrication. Okay. This is for reducing friction between the bones in the knee joint. And then scaling gliding. When you do some gliding motion, okay, so gliding motion in the figure skating, you have to minimize the friction, which means ice here, and then you skate, you glide here. So this one is perpendicular to the ice, okay, and you glide the motion to minimize friction. If then you will be able to easily or better glide on the ice. And sometimes, on the other hand, maximize friction as a source of propulsion. Cleats, soccer cleats. Okay, you get the soccer cleat here, shoes, and then cleats. Okay, without cleats, okay, it will be very slippery on the grass. That's why this is for increasing or maximizing friction. And the skating example, pushing off. Same thing, but when you push off the ice, you have to align your blade diagonally. Okay? This is for maximizing friction, to better propel your body, move forward. Okay, sometimes minimize friction and then maximize friction. And then next kinetic concept is momentum and impulse. So as you can see here, I put these two together. Momentum and impulse. Although these two are different concepts, I put these two concepts together because they are closely related to each other when you have a collision condition. So let's take a look at the linear momentum first. Linear momentum. Linear momentum is the amount of linear motion. You can quantify the linear momentum by multiplying this mass times velocity. Here capital M means the momentum, linear momentum. Here lowercase m is a mass, and then v, the bold v means this is velocity. Simply multiplying mass and velocity will give you the linear momentum. And it's very important in giving and receiving impact and collision, etc. Again, as I mentioned, it's a very important concept when you are dealing with some impact or collision condition. And then this is a vector quantity, which means this one has both magnitude and direction. And the unit of momentum is kilogram times meter per second. Unit of mass is kilogram, unit of velocity meter per second. Okay. So in terms of unit, for the unit, try to understand concepts. If then unit will be given to you automatically. If you start memorizing the unit without understanding the concept, then you will get messed up. So that, for example, here, what's the unit of linear momentum? Okay, linear momentum is linear amount of linear motion. You can get the calculated linear momentum by multiplying mass times velocity. Okay, unit of mass is a kilogram. Unit of velocity is a meter per second. Okay, kilogram times meter per second. That's a unit of linear momentum. Something like this. Okay, try to understand concept. If then unit will be given to numerically. The example of momentum. Okay, we are talking about linear momentum. Momentum, and then there are two hockey players here. They are about to collide with each other. Then I will be applying some linear momentum concept to this example. Okay, M1 and V1. Okay, his velocity, his body mass. M2 and then V2. His body mass, his velocity. So we need to calculate the linear momentum of these two players. So M1. Okay. So first hockey player right here. Mass times velocity, okay, for 50 kilogram per meter per second. This is his velocity, okay, his velocity. And then for him, okay, M2, momentum of the second players, okay, his body mass 80 times 7, so 560 kilogram per meter per second. But this one must be what? Negative. It is moving in the negative direction. Because we always designate this way positive, but the other way is negative, that's why. So here is 450, and then negative 460. Okay? So mass times velocity, this is velocity. Here, I'd like to introduce a very important concept in the linear momentum concept. This is the principles of momentum conservation. Okay, conservation. Momentum conservation. Conservation means something remains constant. Momentum. Linear momentum remains constant under certain situations. So if no external force, if there is no external force, total linear momentum remains constant. There will be no change in linear momentum unless we have an external force coming from outside. Here, no external force, which means, okay, this is from Newton's second law of motion, law of acceleration, so as you learn. If you have no force, okay, again, if you have no force, no additional force, if then this will be zero. Okay? If then acceleration will be zero. So A is equal to F over M, which means if this is zero, then A is also zero. So if you get the A, okay, as you learn, acceleration is equal to change in velocity time over time elapsed. This one must be zero, which means no change in velocity, which means constant velocity. If you have constant velocity, this is constant, and mass is also constant. Constant, or constant linear momentum. That's right. If you have no external force, if then we are going to have constant linear momentum. Let's go over an example of the principles of linear momentum conservation. Okay, this is very important for your the final exam. So you should see this one for your math question. Okay. So there are two hockey players here. Collision. Okay, then we'll be able to apply some linear momentum concept. Okay. According to principles of momentum conservation, momentum before and momentum after remain the same. These two must be equal to each other, right? According to these principles. Okay, total momentum remains constant, which means the momentum before collision must be equal to momentum after collision. Okay? If not, how can you calculate momentum before collision, after collision? Okay, before collision, so you got M1, M2, right? This is coming from the first hockey player, and coming from M2 coming from the second hockey player. This is linear momentum before collision. And then after collision. This is how we can calculate momentum after collision. Okay? We have to add these two players' body mass, because once they collide with each other, they will move together either this way, either this way, depending on who generates a larger momentum. That's why for calculating momentum after collision, we have to add these two body masses and then multiply the velocity. So, and then before collision, after collision must be equal to each other, as I wrote down there. And then momentum after collision, okay, this one is as these two body mass, M1 is from first hockey player, and then M2, and then velocity. And then this one, and this one equal to each other. Okay. Let's calculate actually example. Okay. So right, we have already got their information. Okay. So M1 plus M2 equal to locus M plus locus 2 and the V, right? The V. So M1, his body mass, how much? His body mass was 90 times 6, and then this one is 80 times 7, right? minus. So 550 minus 560 equal to, so mass of this 90 plus 80. So 170 velocity. Right? This is a momentum from this first hockey player, and momentum from the second hockey player. Okay, then this one will be negative 20 equal to 170 then velocity. And if you divide each side by 170, this will be gone. So negative 20 over 170. This will be their final velocity. Their final velocity. What's going to happen to them after they collide with each other? Okay. If we calculate this one, you will get the velocity, certain amount of velocity, but that is a negative, which means they will move together in the negative direction, because second player produced a larger momentum compared to the first momentum. So that here, again, momentum before collision and momentum after collision. And then later we'll be able to identify the velocity, their final velocity. By looking at this velocity, we'll be able to identify which direction they are moving together. So we have to quantify this velocity, and then we have to explain what's going on, what will happen to them by using this velocity information calculated. Okay, this is a example for the final exam. So we will have to go over a couple of problems regarding this later, but again, this is a basic example of principles of linear momentum conservation. And the next concept is impulse. So as I mentioned earlier, impulse is very close to relate to the linear momentum. Okay, let me simply read the definition of the impulse. The accumulative effects of force exertion over a period of time. Accumulative effects of force exertion. We need a force to calculate impulse over a period of time. We need a force and time, which means impulse is determined by force and time. So if you simply multiply force times time, it will give you impulse. Here I means impulse, F means force and time. And this is also vector quantity, like linear momentum. And the unit is Newton second. Why Newton second? Because unit of force is Newton, and the unit of time is the second. That's why Newton second. And then impulse causes what? Change in linear momentum. That's why linear momentum impulse, these are related to each other closely. Because the impulse causes change in momentum. Here I means the impulse. This causes change. The delta means change in something. The change in momentum. Change in momentum means final momentum minus initial momentum. So mv2 final velocity minus mass times initial velocity. It will cause change in momentum. Here equal means these two are using the same unit. But unit of impulse is a Newton second. But however, as you learn, unit of the linear momentum was what? Kilograms times meter per second. This is not equal to actually ns. Ns here in terms of unit, and therefore this one unit, kilogram times meter per second. Or actually ns, Newton second, okay, is equal to kilogram times meter per second, which is a unit of the linear momentum. Because n is actually force. Actually force equal to ma. So unit of m is kilogram. And the acceleration meter per second squared. And then one more time, s is from this one. S. Then one s can be gone. So kilogram times meter per second, which is equal to the unit of the linear momentum. That's why they are using the same unit. That's why we can say, these two are related to each other. Then let me show you how we can get this relationship. Okay. Again. Impulse causes change in momentum, right? final momentum minus initial momentum. And impulse actually F times T. Let me show you how you can draw this relationship. It can come from the second laws of motion, right? So acceleration is actually equal to the change in velocity over time elapsed, right? So final velocity and initial velocity over time elapsed. So you can multiply each by delta t. Okay. If then you can get F delta t is equal to mv2 plus mv1. Okay. Force times time impulse is equal to final momentum minus initial momentum. That's why we can come up with this relationship. Why these two are close to each other. Momentum was changing linear momentum. That's one example of the relationship between momentum and the impulse here. So we have a toboggan race example here. So we have the toboggan race. Okay, this is how they generate impulse to the toboggan. Okay. So there is like a sled. And there are two players here. And then let me just show you how we can do the toboggan race. They push this toboggan as hard as they can, and they jump in the toboggan and the race. Okay, which means they have to maximize impulse until they jump into the toboggan. Okay. So all the information here, and then we need to calculate the final velocity, which means by the time they actually jump into the toboggan, what's the velocity at the point? And then all the information provided here, this force 100 Newton, which is coming from them, okay? Their force. And then they applied this amount of force to this toboggan for 7 seconds. If you multiply these two, force times time, which will give you a total amount of impulse generated by these two players. And then the weight of this toboggan is a mass is 90 kilogram. And then how much final velocity is there when they actually jump into the toboggan. And then we have one more information here. Initial velocity must be 0 meter per second because it stopped initially, right? That's why initial velocity must be 0. So then let's simply just draw this relation Ft equal to mv2 mv1. Okay. Momentum causes the change in, and the impulse causes change in linear momentum. So we got F here, 100 Newton, times 7 seconds. So m is what? 90 times v2, which is our variable interest, and minus m90. v1 actually is 0, right? It can be gone. So the 700 equal to 90 v2. So if you divide this one by 90, okay, answer will be Newton divided by 90 will be their final velocity. When they actually by the time they jump into the toboggan. Okay, impulse will change linear momentum. And then there are again strategies. Sometimes we have to maximize impulse, sometimes we have to minimize impulse, depending on the situation. For example, giving impulse means maximize impulse. For example, the batting. When you the baseball batting, you know. So when we do the baseball batting, okay, when you hit the ball, hit the baseball, okay, hit the ball right here, and then you try to maximize impulse, okay, to send this ball as far as you can. So maximize contact time through follow. So once you contact here, you will apply certain force here, and then during the follow, so you have to increase contact time. So force and the increase contact time, then you will be able to increase total impulse. What if you have you don't do any of the follow through after you hit the ball, after you contact the ball? The ball you just stop. You are not doing any follow-through motion. Which means you're gonna have, if you're gonna have very short amount of the contact time, which will decrease your impulse. If then you cannot kind of hit the ball as that far, okay. And then sometimes receiving impulse, sometimes you have to reduce impulse, okay, by decreasing the time, So from this, again, this is for minimizing the reduced impulse, okay. From actual impulse is equal to f time t, right? Force times t. So you can divide each side by t. Then f is equal to I over t. So by increasing this contact time, you will be able to reduce the force. For example, when you land from again this table. When you land like this, if then you're going to have very short, very decreased or reduced contact time, which will increase very high force. But when you land like this, then you will increase the contact, the time, which will decrease impulse. That's why you do better the land with kind of this posture. Okay, try to increase the contact time to eventually reduce total amount of force acting on your lower body joint. So we can stop here, and then we will do the rest of the Kinetic chapter from the next video.